Our plenary speaker for this probability session is Ofer Zeitouni of the Weizmann Institute and the Courant Institute. I'll just embarrass Ofer with a brief introduction before we get started. So Ofer is a renowned probabilist who has made contributions to a wide range of areas. His areas of expertise include large deviations theory, random walks in random environments, random matrices, and most recently the study of extreme values of random fields, among others. But his broad interests frequently take him outside of these areas and into problems in adjacent fields such as PDE, combinatorics, statistical physics, information theory and statistics. For his contributions, he's received numerous honors. Of these, I'll only mention that this year he was elected to the National Academy of Sciences. I can say that in the field of random matrix theory, he's one of few people who have a grasp on a large share of what is by now a vast field stretching across many disciplines. And we in the field have certainly benefited greatly from his lasting interest in the subject, from his broad experience and for his infectious enthusiasm for its problems. So today he'll tell us about one fascinating corner of random matrix theory that he's been exploring extensively in the past few years. His talk is entitled Stability and Instability of Spectrum of Non-Normal Matrices Under Small Random Perturbations. So take it away, Ofer.
Thank you, Nick. Thanks for the embarrassing introduction. So when choosing on what to speak today, I decided to choose a topic which actually requires very few prerequisites and that has indeed connections to other areas. And let me start with an example of the kind of questions or problems that I will be discussing. So let's take the matrix that is now on the screen, namely, I would call this matrix a maximal nilpotent matrix for obvious reasons. It will play a major role, so let's agree to call it Jn. And now let's look at the eigenvalues. So for this particular matrix, we can all do it in our head because it's easy to write the characteristic polynomial, and all the eigenvalues are going to be equal to 0. But now, suppose you go to your computer and you ask your computer to do the following. You sample a random unitary matrix, and then you conjugate Jn by that random unitary matrix. And then you ask the computer to compute the spectrum and plot it, okay? So of course, we would all say that it's clear, I conjugated the matrix, nothing happens, the spectrum will be at 0. But the computer will beg to differ. The computer will give you this plot. So this is a plot, an actual plot of such a simulation. And it is quite striking because first of all, you see that eigenvalues are not at all near 0. In fact, there is no eigenvalue at 0. And second, most of the eigenvalues are actually very close to the unit circle. And you cannot see it from the plot, but actually very close to being evenly distributed on the unit circle. So, of course, numerical analysts are well aware of that, of this fact, and studies of this kind of phenomena go back for a long time, and in particular, there's a notion introduced, I believe, in this context by Trefethen in the early 90s of pseudo-spectrum, which kind of asks, suppose I add to this matrix a small perturbation, what are the possible values or the eigenvalues? And one way to measure it is by looking at the resolvent of the matrix after the perturbation and asking where are the level sets of such resolvent. So I am going to be interested in a closely related question, which is, suppose I take a small perturbation, a small random or generic perturbation, can I say exactly where will the spectrum be? Before we start to answer that, let me introduce a notion, which is a notion of logarithmic potential. So if you take a probability measure on mu, you can compute its logarithmic potential, which is the integral of the measure against the log potential. This is a function on the complex plane, and it has a nice property that it preserves weak convergence as soon as you have some mild integrability condition. Of course, you need to be able to integrate the log, otherwise nothing would make sense. But if your measure has no problem integrating the log, then the logarithmic potential characterizes the measure, and further, it is equivalent, convergence of logarithmic potentials is equivalent to logarithmic, weak convergence of probability measures. Now, if you have a matrix A, then there is the empirical measure, which is our main object of interest, the empirical measure of eigenvalues, and this gives you a measure on the complex plane. And if you study what does the logarithmic potential of that measure mean, it means that you need to compute a certain determinant. So the logarithmic potential is n times what is written on, this is this log determinant divided by n. Okay, so that's the logarithmic potential. And therefore, in principle, if you want to compute limits of empirical measures, all you need to do is to compute limits of certain determinants. Okay. Now, one other notion that I would like to introduce, if we have matrices, we can think of them as operators, and there is a notion of convergence in a suitable non-commutative probability space to an operator. So this notion is a convergence in star moments. So what is written here is the definition. So if I have a sequence AN and I'm looking at the trace of a polynomial of in AN and AN star, then convergence of that trace to the trace of the same polynomial evaluated on the operator A and its adjoint would mean that I have convergence in star moments. Of course, in order to state that, the operator A has to be there has to be defined a notion of trace, hence the notion of non-commutative probability space. Okay, so maybe a good point to start the story is a theorem of Piotr Sniady from about 20 years ago. And he asked himself, suppose I take a random matrix and I perturb it with a small perturbation, what can I say about the spectrum? So here are the assumptions. You take your matrix AN, suppose it converges in star moments to an operator A, and now add to it a small Gaussian perturbation. So Gn throughout is the matrix with independent IID standard normals, and n to the minus 1/2 is just n to the minus 1/2. N is the dimension of your matrix. And what Sniady showed is that the empirical measure, if you of eigenvalues of An of t, if you take the order of limits in the following way, first you take the dimension to infinity, and then you take the parameter t, the strength of the perturbation, to 0, then the limit is a certain probability measure, nu A, and nu A is characterized by the fact that its log potential is the log potential of the limiting operator A. Okay? So this gives an answer to small perturbations in the sense that it's in principle computable what the limit would be. It also tells you that there is a sequence of regularizations that would bring the limiting spectrum of AN to the Braun measure of A. Now, I'm not going to prove this theorem. There's a beautiful idea in that, which is, since we know we need to compute logarithmic potentials and those involve determinants, the real problem is it's relatively easy to compute traces and expectation of traces, etc. The problem lies in the fact that the log potential involves a log which has a singularity. So in order to tame that singularity, we need some information on small singular values of the matrix AN. And what Sniadny observed is that you can get a lower bound on these singular values by comparing to the singular values of just the noise. And since we know, and those are well known and understood because the noise is just a Gaussian noise. So once you have this coupling, you can get control on small singular values and then just compute convergence of empirical measure of singular values, which is much easier than empirical measure of eigenvalues. And the way he does this coupling is very simple. He looks at the stochastic differential equations that is satisfied by the evolution of the singular values. And he shows a stochastic dominance, a pathwise stochastic dominance. The difference is just the initial conditions. So he shows that if your initial conditions are dominated in stochastic order, this domination will be preserved by the evolution. So this is Sniadny's theorem, and one can now rephrase the question I'm asking by the question, can we take T as function of N in such a way that we can say something about the limit? Now, of course, if you take T to 0 first, the fact that we are dealing with eigenvalues of matrices tell you that the spectrum in the limit will be the spectrum of AN, and that's not at all the Braun measure. So the real question is, at what rate can we take Tn to 0 and still get an answer which is non-trivial and interesting? So this is what we are going to do. So I come back to the nilpotent, the maximal nilpotent matrix I described before. So those have eigenvalue 0, as we discussed. And now, suppose I take a parameter gamma larger than 1/2, and I'm looking at this perturbation. So the important thing to note is the noise. And the fact that gamma is larger than 1/2 for officianders of random matrices, I should immediately see that the norm of the matrix n to the minus gamma gn goes to 0. So what we are doing here, we are doing a perturbation of Jn by a matrix whose norm goes to 0. Now, if Jn were Hermitian, then we know that the perturbation would do nothing to the eigenvalues in the limit, because the perturbation is weak and we have stability of the eigenvalues. But here we are still getting a small perturbation, but Jn is not Hermitian, is as far from Hermitian as possibly it can be. And the theorem, which was proved 6 or 7 years ago by Alice Guionnet, Philip Wood, and myself, says that the limit is what you saw in the simulation. namely the empirical measure of eigenvalue converges weakly to the uniform measure on the unit circle in the complex plane. There's an earlier version of this theorem which identified the limit locus by Davis and Hager. All these small pictures that you see at the top of the slide are pictures of the people involved that I have downloaded from the internet. So you can, if you're too bored, you can try to guess who is who. This theorem has a generalization to IIDGN, which was proved shortly after by Philip. And this is a simulation. This particular simulation has real noise, as you can see by the fact that the eigenvalues come in pairs. Okay, now it's pretty easy to explain what is going on. The fact that the spectrum is not stable, you can illustrate in the following way. Look at the matrix J and delta. The only difference between Jn and J and delta is this element here on the left corner, delta n. This perturbation is simple enough that you can write the characteristic polynomial. And the characteristic polynomial is z to the n plus minus delta n, where the plus minus depends on parity. And the roots of this characteristic polynomial are written here. They are just the roots of unity multiplied by delta n to the power 1 over n. And you see that if delta n goes to 0 polynomially, then delta n to the power 1 over n goes to 1. And therefore, you will have that the eigenvalues of this particular matrix converge to the empirical measure converges to the uniform measure on the unit circle. Okay, so this immediately begs the question, why, when we add noise, does the noise choose this particular perturbation? Because if I do other perturbations, they will definitely not give the same answer. So how is it that the noise chooses this particular perturbation? And in fact, there's a general criterion for that. I don't want to explain exactly the notions, but basically it says that if your operator A, the limiting operator, is nice in the sense that it does not it is not atomic on some region, and if you converge in star moment to this limiting operator, and if your empirical measure of eigenvalues converges to the same Brown measure, then once you perturb AN, nothing changes. So this is a stability theorem. So I would call this theorem a stability theorem because it says that if you converged to a measure nu A without perturbation, then you converge to the same measure even if you add a perturbation. Okay? Now, you would be justified in asking why is that of interest at all? Because in our situation, we know that this condition, the condition that ln A converges to nu A for our operator is just a uniform measure on the unit circle. So this condition is not satisfied because this condition, in our case of Jn, ln A just converges to the Dirac at 0. So why is this theorem useful at all? So the reason is that we also proved the second theorem under the same assumption. And that second theorem tells you that if you find a polynomially vanishing perturbation such that after you added that polynomially vanishing perturbation, you still converge, you now converge to the right limit, to the Brown measure of A, then once you add a noisy perturbation, you will converge to the same limit. So somehow this tells you that the noise knows which perturbations to choose. It will choose exactly the perturbation, if such a perturbation exists, that gives convergence to nu A. Okay? So I'm seeing there is activity on the chat, which I don't see in parallel. I'm assuming that there are no remaining questions, but if there are, it's a good point to pause for that.
Well, maybe this one right here. Toeplitz asks, which of the two theorems is stronger?
So it's, of course, the second theorem is generalizes the first because you can take En equals 0. So the second theorem has as a particular case the first theorem, but the interest in the second theorem is that you can choose any En and you will get that result. Okay, so in our example, in the example of Jn, we choose En to be the n1 element, which means we chose En to be n to the minus delta here and 0 everywhere else for any, and actually any delta would work. Okay, this would be a vanishing perturbation and it will make this condition work. Okay, good. So the next question is, maybe it always works. Maybe always we can find such a perturbation, and the answer to that, unfortunately, or maybe fortunately because it makes the area interesting, is that no, there are examples, some of them analyzed in joint work with Ohad Feldheim and Elliot Paquette, that show that actually the answer is different. You converge in star moment to A, but actually the limit of the noisy perturbation is not nu A at all, something else. Okay, so having said that, what can we say, and what can we say in some generality? So a natural model which is related to that maximal nilpotent model is a model of Toeplitz matrices. So here you see some simulations. So this is an example that I will refer to as a limaçon. So here we are looking at Jn plus Jn squared, which means that we are looking at the matrix which has 1 on 2 diagonals above the diagonal. And what you see in the simulation on the left is a matrix plus noise with 3 different levels of noise. So I remind you that the noise is n to the minus gamma Gn. So there are different values of gamma according to the colors. And on the right, you see a computer trying to do a random conjugation. So the computer here is as silly as it was in the beginning, in the sense that, of course, the conjugation changes nothing, and the spectrum of this matrix is still at 0. But the noise pushes it away. And here you have other examples. So again, the blue on the right are computer attempts to compute randomly conjugated. The left is noisy versions. What you see on the left are the top one is a matrix in which you have on the same Jn, but on the diagonal, you go from -1 to 1 in a linearly interpolated way. And on the bottom, what you see is just IID elements on the diagonal and 1 above the diagonal. So what I find striking in these, there will be in a theorem in just a second, but what I find striking in these is that, again, this phenomenon of instability of numerical algorithms is completely explained by noisy perturbation, although we don't have a theoretical justification. So here is a theorem. The theorem, which is joint work with Anirban Basak and Elliot Paquette from a few years ago, says that if you take the IID uniform case, then the empirical measure converges to something explicit, and the log potential of the limit, you can write it explicitly in the way that I wrote here. And it gives the spectral curves that you saw in the simulations. The second theorem we proved is that if you take an upper triangular Toeplitz matrix with a finite symbol, so the symbol for a Toeplitz matrix, so a Toeplitz matrix will have, say, A0, A1, up to AK, and all the rest would be 0 if it's upper triangular. And the symbol then is just sum of AI Z to the I from 0 to K. So this we refer to as a symbol. And the empirical measure of this, so again, this Toeplitz matrix, of course, has all its eigenvalues equal to A0. However, when you add noise, what you see is the law of this sum. So another way to state that is that the law of the limit is just the push forward of the uniform measure on the circle by the symbol. Okay? So this is a push forward. Of delta S1 by symbol. I'm hearing some whistle in the background. Is it because someone is unmuted? No? Okay. So this, it turns out, extends also to twisted Toeplitz matrices, which means matrices where the diagonal changes slowly along the diagonal. So this is the example of the stadium. What you saw with the stadium is exactly, so the stadium means the matrix which started from -1 here and ended at 1 and had all ones here. What you saw, maybe I will go back to the simulation. So what you saw in this stadium is exactly a uniform measure on the circle moved continuously between this center and that center. So this gives this picture or this picture, it's just that theorem, okay? So first of all, I should say that this confirms some simulations and predictions based on pseudo-spectrum that appeared in work of Trefethen and co-authors. Some two-diagonal cases were studied by Sjostran and Vogel, and I will return to their important approach a little bit later. Now, the underlying idea in the proof of that theorem is the following. Suppose I have a general matrix Mn, and I shift it by Z, and I write its singular value decomposition. So the singular value decomposition of the matrix Zi minus Mn will have a unitary, two unitaries U and V, and a diagonal matrix Sn, sigma n, which is the matrix of singular values. And by convention, I'm going to arrange them non-decreasing. And suppose that I can split my matrix in two, the small singular values, what I call Sn, which has a dimension n star, and the large singular values or big singular values, which I call Bn. Now, I didn't quantify what does large and small mean. So here is a quantification. N star is just essentially separating between small, polynomially small singular values and larger ones. So suppose I have done that, and now I'm looking at the log determinant of my noisy matrix Tn. So the theorem is that this log determinant erases the small singular values Sn and looks only on the block Bn. But remember, the matrix Mn is deterministic. So this statement tells you that when you add a noisy perturbation, you will pick up a deterministic limit. And now the only issue, if I give you a particular Mn, is to study the singular values of Mn minus Zi. And in the case of Toeplitz matrices, there are methods to do that by means of transfer matrices. So once you have this theorem, which is actually not very hard to prove, it all boils down to a study of transfer matrices, and okay, this is more complicated and tedious, but the basic theorem is this one. So again, this theorem tells you both a stability and instability result. It tells you that, of course, the spectrum is not the same as the spectrum of Mn, or the logarithmic potential is not the same as the logarithmic potential of Mn, but all you have to do is to remove the small singular values from Mn, and then you're fine. And then everything is stable. Whatever noise you add in the limit, you will converge to that. Okay? And in the cases that I described, one can indeed study the singular values. I'm not going to discuss that. Now, this theorem worked in the way that I stated. That theorem worked only for Gaussian noise. So not only Gaussian noise, but actually complex Gaussian. So it's really limited. And the reason it was like that is that the very first step, we changed basis. And the nice thing about Gaussian complex matrices with IID entries is that the change of matrix does not change the law. A change of basis does not change the law. So once you change basis, you can bring yourself to this triangular matrix plus Gaussian, to this, diagonal matrix plus Gaussian, and then everything boils down to studying that. But in fact, the theorem is more general. The theorem is for Toeplitz matrices. You can generalize that. So the generalization just involved two conditions on the noise. One is a condition on the Hilbert-Schmidt norm of the noise matrix. And the second is a condition on small singular values of Mn plus the noise. And for Gaussian matrices, this has been studied at least since the work of Spielmann and Tang and others. For non-Gaussian matrices, it is now well understood how to control such small singular values, and most models of certainly matrices with IID entries satisfies these kind of conditions, and there are now a lot of models of noise that satisfies this kind of condition. And under just these two conditions, the theorem I told you about convergence of the noisy version of Toeplitz matrices applies here as well. So this is kind of an optimal result in that respect. I'm going to, I see that time is running faster than I hoped. I hope to show you something about the proof, but I'm going to skip there. I only want to mention that there's a different method which was developed to handle the same question by Shostran and Vogel, and I will describe the method in a little bit. Okay, so let me skip this proof ingredients and go exactly to this alternative method, which goes by the name of the Grushin problem, which was introduced in the context of differential operators. So what is this method? Suppose I have a matrix with singular values T1 up to Tn. And I want the eigenvalues of A plus delta G, where G is some arbitrary perturbation and delta is small. So I can introduced two bases. We saw that singular values are important, so why not also discuss singular vectors? So those are EI and FI, depending on whether I look at A star A or A star. Of course, this FI and EI are exactly the matrices U and V that we saw earlier. And suppose now I also call delta I to be the standard basis. Now we're going to fix a parameter, M, which is going to measure how many small singular values A has. And once we have that, we're going to augment the matrix A by certain matrices. So we are going to introduce a matrix P, written here, as an operator on a larger space of dimension n plus m. And this matrix is going to be, in general, a bijection if A is invertible. And suppose that P is invertible, we can introduce the inverse and we can compute it. And the inverse can be written explicitly in terms of this EI, FI, delta I, and the singular values of A. And the nice thing is that we have a priori norm estimates on the matrix. There is one thing, one parameter alpha that I have not emphasized and that I should emphasize. So alpha is the threshold of truncation M. So M are going to be all eigenvalues, all singular values, except for the first M, are going to be larger than alpha. So this is a choice. And once you do this choice, you can check that what I wrote here is correct. But what we are interested is not on the matrix A, we're interested in the matrix A plus delta G. So once you apply to that matrix, the matrix P minus 1, you can get an expression for P delta E. And what is more important, you can get an expression for the inverse of P delta. And the inverse of E delta can be written in block forms, and you can get control on the norms of the blocks. So again, in spite of the fact that you added noise, you can use perturbation theory if your delta is small enough. So if this condition is satisfied, and in our application, it will always be satisfied, or almost always, then you can get norm control on the blocks of E delta. Okay, so those are just algebraic manipulations. But the point is that if you now apply the Schur complement formula to P delta and E delta, so on the one hand, when you apply it to P delta, you get that the determinant of P delta is related to the determinant of A delta times a certain error matrix, which is this matrix here. Okay. Right here. On the other hand, by using the equation defining E delta plus, you can see that E delta plus is exactly related to the matrix A delta inverse, and therefore, because R plus E delta plus, remember that E delta plus is, E delta is the inverse of E, so it relates to P delta, and from that inversion formula, you can write back what is that matrix, and the matrix that appears here is exactly appearing also in this relation, which means that the determinant of that is a determinant of E minus plus delta. So the important thing is that the determinant of the noisy matrix, which is P delta, can be related to the determinant of the top left corner plus multiplied by the determinant of this beast here, E minus plus delta. So in particular, this gives you that the log of A delta, which is what we cared about, the log of the determinant of A delta, is the log of the determinant of P delta plus a perturbation which we control. And in particular, to see this control, if you look at the log of determinant of P delta, you can, of course, differentiate with respect to the parameter delta. You can write it in terms of the matrices E and the derivative of P, which is just G. And what you obtain is an object that has to do with the norm of G and that parameter alpha. In particular, with a judicious choice of alpha, this quantity will go to 0. And in that situation, this divided by n will go to 0. And in particular, this tells you that you can compute the log of this matrix in terms of the initial matrix, P0, which is explicit because it does not involve the noise. And that's what I'm writing here. So in particular, you can relate the log det of P delta to the log det of P, which you can compute. And in particular, you can relate the log det of A delta to the log det of P plus an error term, which comes from those errors, which we are going to take to 0. The lower bound is very similar. I'm not going to write it here.
Ofer?
Yes.
Is there some meaning to the imaginary part of this integral, which is not being used?
I'm not sure. In fact, if you are working with real noise, there would be no imaginary part, right? Everything would be real.
Okay.
Yeah, I don't know. I don't know on the top of my head. Okay, so this tells you that the log determinant of A delta, which is the object we care about because this gives us the logarithmic potential, can be written in terms of a perturbation of your original matrix, an explicit deterministic perturbation. And this is exactly the analog of the deterministic equivalence lemma that I showed you earlier for Gaussian noise. So this works for general noise. It's actually quite general. So it's contained in a short note of Martin Vogel and myself, short one. Okay, now let me switch gears to two topics I would like to mention. One is outliers. So necessarily I'll be a little bit telegraphic, but for the aficionados for the probabilistic crowd, as opposed to the matrices crowd, there are some surprises here. So we said something about convergence of the empirical measure, but you can of course look not just on the empirical measure, which converges to this limiting spectral curves, but you can look at the eigenvalues which are not converging, those that are away from the spectral curve. And what you see here are two simulations of such situations, so in the purely nilpotent case and in the Limassol case, and you obviously see some kind of process happening inside. And you could ask, what is the structure of this process? What are these outliers? And let me immediately tell you the answer. So in this case, the outliers are just the zeros of a limiting Gaussian field. So this is what one would guess a priori. Before I proceed, before I forget, I should mention that the study of outliers has some history, and in particular, there has been work not with vanishing noise, but with actually rank 1 or finite rank perturbations. So there has been work of Tau, and there has been work of Capitaine and Bordenave and others on outliers for random matrix models. So this is in the same type of questions. The tools are, however, very different, as I will try to show you, the tools to get the answers. So in this case, you do get a Gaussian field, but in the Limassol case, you actually get something quite interesting. So you can write the matrix as a product of two by just decomposing, looking at it as a polynomial and decomposing it. And what you see is that there are no outliers in this region. And then there is a region where the two eigenvalues those are just the eigenvalues of the polynomial x squared plus x plus z. Those are what are lambda 1 and lambda 2. They are just the roots of this equation. And in this region, right here, again, you will find a Gaussian field. And this field will have some coefficients multiplying Gaussian variables. On the other hand, in this region, you get a field which is not Gaussian at all. In fact, it's a field whose coefficients it's a sum of polynomials in the lambda 1 and lambda 2 with coefficients which are products of Gaussians, so not Gaussian at all. And in fact, there's a general answer, so I will only flash it. So you can do the same computation in general. You can rewrite your symbol in terms of this lambda I of z, and then split according to how many there are which are larger than 1 or smaller than 1. So this is these regions, dk. And if you look at the infinite band Toeplitz operator with that symbol, and you look at the empirical, then it has a spectrum d infinity, and that spectrum turns out to exactly equal what we find at limiting spectral curve, which is A of S1, together with a region where this parameter d is equal to 0. This is exactly where it is not equal to 0. This is exactly the region in the complex plane where the symbol has a non-zero winding number around z. Okay, and the general theorem is that in the region of no winding number, there are no eigenvalues. So in the particular, in the case of the maximal nilpotent, this is the interior of the disk. In the case of the Limassol, it's the outer envelope of the spectral curve. There are no eigenvalues, no outliers there. On the other hand, there are regions which correspond to these different winding numbers. And on each of those, you get a different fields. Those fields are just polynomials in the lambda I, and the coefficients of these polynomials are specific minor of the noise matrix, of a size which has to do with the winding number. So again, in the case of the maximal nilpotent, the winding number is 1. So the minors are of size 1. Hence, you get a Gaussian process. And the zeros, the outliers are going to be in laws the same as the laws of the roots of this Gaussian analytic function. In general, it's going to be an analytic function. This we can prove. It's not going to be Gaussian. And the roots are going to, the outliers are going to be roots of those fields. Those fields, unfortunately, have a rather complicated combinatorial, explicit but complicated combinatorial description, which I'm not going to bother you with. And I find it an interesting class of processes. I don't know much about them besides their existence and their description. Okay, so this we already said. In the particular case of the Gaussian complex noise, you recover a Gaussian analytic function, a hyperbolic Gaussian analytic function, which is well known from the study of random Gaussian analytic functions and polynomials. In particular, you can compute the intensity, the first intensity of the limiting field, and that intensity had also been computed by Shostran and Vogel by the approach. Okay, just to give you an idea of how this is done, the basic idea is that you develop the determinant of Zi minus Jn minus noise, and you try to identify in the development the dominating terms. So in this case, let's say if you are in the case of Jn, and you are inside the disk, this is going to be exponentially small. And this remainder is going to be polynomially small compared to the main term. Once you prove this, that the remainder term is exponentially small compared to the main term, it's not very hard using Grushin's theorem to check that the zeros are going to be the zeros of this part. And here you identify the field that I described. Okay, so this is a limiting field that I described. Okay, the last topic I wanted to touch upon is some work in progress, which is a question about eigenvectors of perturbed Toeplitz matrices. So this is the same maximal nilpotent matrix. Those are simulations that Elliot ran a few years ago, Elliot Paquette ran a few years ago. And you see here the eigenvalue corresponding to one particular, the eigenvector corresponding to one particular eigenvalue. And I think that these pictures are striking. Namely, you see several things. So those depend on the noise. So here you have gamma equal 2, gamma equal 1.5, and here you have 0.9 and 0.75. So something is happening. It's clear that something is happening. First of all, it's very regular for small noise, and as you increase the noise, you start getting a wild eigenvector, maybe delocalized in the usual sense. So this hints at a phase transition. So at the moment, we can prove this picture completely in the case of the maximal nilpotent, and we can deal with a case gamma larger than 1. So this is this ordered phase in quite general setup. And the key is to go to that Grushin problem. You can by now realize that I'm a convert to this point of view of Shostran and Vogel. Not everything can be done by it, but it's a very nice device for capturing the algebraic structure of the problem. So I remind you of the setup. We have this P, which is an augmentation of our matrix A by this finite, by this M size perturbations. And now when you look at the perturbed Grushin problem, this P delta and its inverse, this introduces the matrices E delta that we have met before. But the key observation, there are two key observations. The first one is that if this matrix is invertible, if the matrix I plus delta QE is invertible, you can represent this lower right corner, which was important for us because this is exactly the quantity we bounded before. You can represent it in terms of the inverse of your original matrices. So that's one thing. Here, everything is rather explicit. There's a noise matrix here, and there's a matrix E, which is completely deterministic given by your original matrix A. So that's one thing. But the more important thing is that E plus, this quantity here, is a bijection from the kernel of this matrix to the kernel of A delta, which is what we are interested in. We are exactly interested in the kernel of A delta. And the inverse of this kernel is actually deterministic. It's an unperturbed operator. So this means that if we understand the kernel of this matrix, we understood everything. And the kernel of this matrix is given in terms of the deterministic matrices E minus plus, which is written here, so it's a very explicit matrix, and a matrix here which involves random matrices, because Q is random. Okay, so what happens once you agree to these two facts? Well, if you take AN to be Jn minus ZIN, our good friend, and Q Gaussian IID, then depending on gamma, you pick up the M in the proper way. So this turns out to be a proper way. And here is what happens. So first of all, we know what Z is. We can go back to our analysis of outliers, massage it a little bit, and we know where the eigenvalues are going to be. The eigenvalues are going to be at some distance from the unit circle, very close to the unit circle, but at some distance of order log n over n. Further, there is a particular vector of norm 1, which has a nice property that AV is small. And this particular vector, we will call it the pseudo mode associated with our matrix. So it's a very explicit vector. Once you know your eigenvalue, Z, you can write down this vector explicitly. It has a decay at scale n over log n. So this is consistent with the picture I showed you in the beginning. And the easiest case is when gamma is large, which means the noise is small. Then delta Q is tiny. Then this matrix is essentially the identity. Then this is just a small perturbation. And everything is given by the kernel of E minus plus delta, which is essentially the unit vector, which then is pushed by E plus delta to the pseudo mode. So that's the easiest case. If gamma is between 1 and 3/2, it is not true that this matrix is small. So you cannot use the fact that I plus delta QE inverse is essentially I. But with high probability, it is invertible because it's just a noisy Gaussian perturbation of a deterministic matrix. We have an a priori inverse on the norm of the inverse. And we can do an expansion, a resolvent expansion. And this is a resolvent expansion, delta EQ E plus, delta square EQ square E plus, etc. And the point is, now comes the random matrix analysis. You can check that the norm of that is small. So in fact, in spite of the fact that this matrix was not invertible, this whole object is small. And because it is small, you get the same conclusion as for gamma larger than 3/2. The difficult region is when gamma is smaller than 1, then the norm estimate completely fails. So we need to take a larger M. And when we take a larger M, the eigenvector is a random combination of singular vectors of A minus Zi. How many singular vectors? Exactly M of them. And what you get is a field, a stochastic process, which has a random combination of these singular vectors. And you can check that the correlation length of this stochastic process is of order n to the 2 gamma minus 1, which is a power of n, because gamma is smaller than 1, but larger than 1/2 in all our story. So this is a negative power of n. So you get a process that gets wilder and wilder as gamma goes to 1/2. And this is completely consistent with the picture of the simulations. So you see that as gamma decreases, in this regime of gamma less than 1, the process becomes wilder and wilder. So as I said, this is work in progress. It's completely understood for Jn, the maximal nilpotent, and we will see how far we can push it in this region gamma less than 1 for general models. I have cheated you in one point that I just want to square with you on that. So the norm estimates I mentioned were for deterministic Z. In our situation, Z is a random eigenvalue, so you cannot use, it's not so simple to do the norm estimates. However, you can use an appropriate net of Z's and a good probabilistic estimate on the norm to bypass this issue. Okay, so some concluding remarks. So one item that I have left open, I showed you things for twisted Toeplitz symbols. I remind you, twisted Toeplitz symbols are like Toeplitz matrices, but where the diagonals change slowly, like the stadium. In the upper triangular case, we showed that this is a mixture of push forward of the local symbols. We expect it to be true in general. There are some partial results of Martin Vogel, and you can, in the case where it's a twisted symbol that such that the diagonals are continuous, namely that let's say that they have zero boundary conditions in the top and bottom, you can actually prove it either by Martin's results or by our methods, but the general case is still not settled. For Toeplitz symbols with Toeplitz matrices with infinite symbol, it depends on the rate of decay. There's a beautiful paper of Shostron and Vogel in that case for fast decay, and the slower decay is not yet clear. I discussed already the problem of eigenvectors. And to me, the most interesting question is what actually happens in numerical algorithms. So I showed you certain numerical algorithms, but all my theorems were for random perturbations, quite general random perturbation, but still. I think it would be very interesting to understand to what extent the actual numerical algorithms mimic these random perturbations. Okay, I will stop here. Those are some references. Thank you for your attention.